This is section 3.7, higher derivatives, objective 2, which is to compute higher derivatives in a variety of scenarios. When you're done, I'd like you to be able to write one main thing you need to remember to do when trying to determine a formula for the nth derivative of a function. So if we look at example 1, each of these is just going to require us to do the first and second derivatives. So you will notice that sometimes I will simplify and sometimes I won't. And it depends on whether it gets more complicated or not when I try to simplify. On this one, if I want to take the first derivative, I will apply the quotient rule, which is low d high minus high d low. Might help if I actually do that. Minus high d low over low squared. Now, if I were just taking the first derivative and this were a free response, I could leave it as is. However, I want to take the second derivative of this. And when we take derivatives, we always have the option of simplifying first before we take the derivative. And as I look at this, that top looks pretty complicated, pretty messy. So rather than taking the derivative with it written this way, I'm going to simplify. I'll get a 6 minus x squared plus a 2x squared. And I'll leave the bottom the same because it looks pretty nice as is. And I can see that I'll end up with an x squared plus a 6 over a 6 minus an x squared quantity squared. So now this looks pretty derivative friendly. So if I take the derivative again, I can use the quotient rule. So there's low d high minus high d low. Notice with the low I'm going to have to do the chain rule. I bring that 2 down in front to the first power, and then I multiply by the derivative of the inside all over this low squared. And because I don't have to take the derivative again, I'm going to leave it as is. If we look at this next one, we have f of x equals the tangent times the sine. So my derivative would be the first one times the derivative of the second one plus the second one times the derivative of the first. Now I could simplify if I chose, because tangent is sine over cosine and the cosines would cancel, and I'd get a sine of x plus a sine of x times a secant squared. I could leave it like this and differentiate, or I could even factor so that I just have to do the product rule once. So if I take the derivative again, I will have the first one times the derivative of the second plus the second times the derivative of the first. So the derivative of the second, I'll get a 0 plus I hit the power, so that's a 2 of those secants, times the derivative of a secant, which is another secant, times a tangent. And again, since it's the second derivative and I don't have to derive again, I can leave it as is. With part C, again, we have the product rule. So we can write f prime will be the first one times the derivative of the second plus the second times the derivative of the first. And I could continue on to take that second derivative, but it would require that I do the product rule twice. So to simplify that and avoid having to do it twice, I could factor that e to the x out, and then notice that I just have two things being multiplied together. So I could do the first one times the derivative of the second plus the second times the derivative of the first. Now on this one, this would probably show up as a multiple choice problem, so they would probably factor that e to the x out and combine some like terms. It looks like I have an x squared, I have 2 of those 2x's, and I have a 2. So this one most likely would be simplified. If we look at example 2, the goal is to come up with a pattern and then use the pattern to compute the 34th derivative. So 34th derivative, that's going to take us a long time unless we can see the pattern. So if I take the first derivative, I get a cosine. If I take the next derivative, I get the opposite of the sign. If I take the third derivative, I get the opposite of the cosine. And if I take the fourth derivative, we get back to where we started. So now I'm back up to here again. So this would be the same as my 5th, 6th, 7th, and 8th, 9th, 10th, 11th, and 12th, 13, 14, 15, and 16th. So every 4 with these sine functions, every time I take a derivative 4 times, I'm back where I started. So if I want to compute the 34th derivative, that's going to be just like the remainder of 34. If I divide the 4 out, I have a remainder of 2. So that's going to be the same thing as the second derivative. And that second derivative is negative sine. With part B, it's going to be similar to part A, except that we have to pay attention to the fact that we will be using the chain rule. So if I do my first derivative, I will hit the cosine, and then I will hit the inside. Now this is the same as a negative 2 times the sine of 2x. So when I take the derivative again, I will move through that negative 2 and then hit the sine. So I'm going to keep it like this instead of moving it in the front, and just keep in mind that that is going to be a constant, so it's not going to change. So as I hit the negative sign, I'll get a negative cosine of the inside unchanged. I still have that 2, and now I need to multiply by the derivative of this inside, which is going to give me another 2. If I look at my third derivative, then I will have the opposite of the cosine, which is a positive sign. And again, I multiply by another 2. And with my fourth derivative, notice that I've looped back around to that cosine that I had, but what's extra is this 2 to the 4 at the back. So if I want the 34th derivative, we're going to use the same fact that we have a multiple of 4 with a remainder of 2. So we're going to be like the second derivative, except at the back we will have a 2 to the 34th. If we continue with part C, again we want that 34th derivative, then we're going to need to look for a pattern. The first derivative, notice I'm doing the product rule, will be the first times the derivative of the second. Notice I hit the e, left it alone, and then I multiplied by the derivative of the power. So here was my first times the derivative of the second, plus the second times the derivative of the first. Before I take the derivative again, I'm going to factor that e to the negative x. And notice that I have a negative x plus a 1. Now if I do the next derivative, I'm going to do the product rule here. So I'll have the first one times the derivative of the second plus the second times the derivative of the first. Again, if I factor out the e to the negative x, we can see that I'll have a negative 1 plus a negative 1 times a negative x is an x, and a negative 1 times a 1 is a negative 1. So I end up with an e to the negative x times an x minus a 2. So let's try it again. Third derivative, I'm going to keep doing this until I start to see a pattern. Third derivative, I have the first one times the derivative of the second plus the second times the derivative of the first. Factor out the e to the negative x. I have a 1 minus an x plus a 2. So I get an e to the negative x times a negative x plus a 3. Now some of you may see a pattern already, some of you may not. So let me go one more time to see if the pattern becomes more obvious to everybody. We have our first one times the derivative of our second plus the second times the derivative of the first. If I factor out that e to the negative x, I'll have a negative 1 plus an x minus a 3. So now I've got e to the negative x times a positive x minus a 4. So if we look at this list, we can kind of see that the x's are changing from negative to positive, from negative to positive, and I'm either adding 1, subtracting 2, adding 3, subtracting 4. So hopefully you can see that the 34th derivative will have that e to the negative x out in front, and because it is an even number, we're going to have the even pattern, which is a positive x in front, and then we subtract what derivative we're on. In this case, it's the second derivative, so we subtracted 2. The fourth derivative, we subtracted 4. The 34th derivative, we subtract 34. With example 3, we want to generalize a pattern algebraically to find a formula for the nth derivative. So what's really important when you do this is that you don't simplify too soon, because you'll fail to see the pattern. It gets much more complicated if you simplify as you go along. So what we're going to do is we're going to start with the original, and then we're going to take the first derivative, and then we're going to take the derivative again, and we will not simplify. Then we'll take the derivative again, and we won't simplify. So notice these are constants, so we're just moving through them, and then we're hitting the power rule. So we bring that power down in front and decrease the power by 1. My fourth derivative will be n times n minus 1 times n minus 2 times n minus 3, and then I'm raising to the n minus 4. So if we continue this pattern, we can see that the mth derivative, that means when I'm at a place that is smaller than n, I'm going to start with n, go to n minus 1, then n minus 2, and I'm going to keep that multiplier until I get to the last one, and then it'll be x to the n minus something. So what I want to do is I want to see if I can identify the pattern here. Here I'm subtracting 1 on the first one, I'm subtracting 2 on the second, 3 on the third, and 4 on the fourth. So on the mth one, I'm going to subtract an m. Now let's look at where we end. Here, with the second derivative, the last number I subtracted was a 1. With the third derivative, the last number I subtracted was a 2. And with the fourth derivative, the last one I subtracted was a 3. So that means with the mth, I'm going to subtract 1 less than m. So if I continue even further, because I want the nth derivative, then I will have this n times an n minus 1, and I'm going to keep going down until I subtract my last thing, which is the n minus 1. And the exponent will be an n minus an n. Now that I have the pattern, I can simplify. This n minus an n minus a 1 is actually a 1. So I went from n all the way down to 1. Hopefully you remember that that's an n factorial. And then x to the n minus n is x to the 0, which is just 1. So we end up with the nth derivative being n factorial. With b, again, we want to continue to take the derivative until we see the pattern. My first derivative will be hit the e, hit the power. The second derivative is going to leave that constant alone, so it'll move through it, hit the e, hit the power. So now I've got a 2 squared e to the 2x. With my third derivative, I'll move through the constant, hit the e, hit the power. Now I have a 2 to the third e to the 2x. Hopefully you see a pattern. We see that the first one had an exponent of 1, the second one was an exponent of 2, the third one was the exponent of 3. So the nth derivative will be 2 to the n times e to the 2x. So let's look at part C now, which is a little bit tougher. To make this easier, I'm going to rewrite this as a 5x minus 1 to the negative 1. If I take the first derivative, I'm going to apply the power rule first. So I'll bring that negative 1 down in front. I'll subtract 1 from the power, and I'll multiply by the derivative of the inside. Now to make this easier, I am not going to simplify. So when I multiply the next one, or when I take the derivative of the next one, I'll bring this negative 2 down in front, leave the inside unchanged, reduce the power by 1. That 5 is a constant, so it's still there, and now I need to multiply by the derivative of that constant. If I do the third one, don't simplify. Notice that I still have this constant at the back, and then I get another 5. So now let's do the fourth one. Hopefully we have enough now that we can detect a pattern, because I want a pattern for the nth derivative. Well, let's look at what's the same. We can see that this 5x minus 1 is the same for all of them. We can see that the power is actually 1 more than the derivative number, and then we change the sign. So that means I could take the n plus the 1 and then change the sign. That would work because if I have a 4 plus a 1, that'd give me a 5, change the sign. A 3 plus a 1 gives me a 4, change the sign. So if I have the nth derivative, I'll add 1 and then change the sign. If we look at the back, we also see that I've got these 5s, and their exponent is the same as the derivative that we're on. So that would have a 5 to the n. If we look here, it looks an awful lot like the n factorial. The only thing that's missing are the negatives. So here we've got 1 negative, then we have 2, then we have 3, then we have 4. So I could say I have a negative 1 raised to the nth power. So now I have an nth derivative pattern that I can use. For our last example, example 4, it involves an application of higher derivatives. So we've seen this before, but now we're wrapping back around to get the same thing again. The position is given by this function. I'm interested in the velocity. So the velocity, if you recall, is the derivative of the position, which will be a 6t squared minus a 30t plus a 36. Next, we want to find the acceleration. Well, the acceleration is the derivative of the position, or excuse me, derivative of velocity, or the second derivative of the position. So we take the derivative, we'll get a 12t minus a 30. With part C, we want to find the particle's acceleration after 1 second, so that means we just plug a 1 into the acceleration curve, and we get a negative 18. And last, we want to find the acceleration when the particle is at rest. So to be at rest, that means the velocity is 0. So to find those times, we need to factor this velocity function. So I pull the 6 out and factor the rest of the way. Looks like t minus 3 and t minus 2. So we're at rest when t is 2 or when t is 3, and I want the acceleration at each of those times. So I'll plug in a 2 and I'll plug in a 3. If I plug in a 2, I have a 12 times a 2 is a 24 minus a 30, which is a negative 6. And if I plug in a 3, I get a 36 minus a 30, which is a positive 6. So I'm either pushing to the left with a magnitude of 6 or I'm pushing to the right with a magnitude of 6. Okay, I'd like you to look through your notes web exam problems and look for the ones that you don't know how to do so that you can ask questions. And then based on the examples I've done for you, I want you to write the one main thing you need to remember to do when trying to determine a formula for the nth derivative of a function.